Welcome everyone to this 22nd session of Statistical Learning in Practice. Today we're going to finish off time series, and so we'll see estimation, inference and forecasting in ARMA models. And we are going to put these into practice in the practical next week. And then just as a reminder, on Wednesday next week, we'll have a Q&A session rather than a theory or practical session, because we're done with the contents of the course. And I will cancel the office hours. I will not hold the office hour on that Wednesday. If you are in a time zone in which you cannot attend the session on Wednesday next week and cannot ask questions but have them, then just drop me an email and we can chat about it. Okay, so 3.3 estimation, inference, forecasting in ARMA or ARIMA models. Let's just say ARMA for now. I mean, we are, as part of the following, going to test whether the data arises from an ARIMA model, and then if this test is positive, or if it is, say, that we have an ARMA instead of an ARIMA, in the sense of saying that ARIMA, it has this coefficient D larger than 0. Then if we are ARMA under this setting, then we can estimate and make inference. And if we're not, then we can transform it into an ARMA process and then do estimation and forecasting. Okay, so then estimation and forecasting are really for ARMA processes, and then inference is a combination due to that. Okay, so 3.3.1, I guess. 3.3.1. So this is estimation. Okay, so let's begin with an ARMA process, as I was just saying, for estimation with orders P and Q, and we're going to make several assumptions. So we're going to assume first that it is Gaussian. Okay. So what does this mean? Well, I think we've sort of discussed it. This means that the white noise that defines the ARMA process satisfies that the epsilon t's are, they're not only uncorrelated, but the IID are normally distributed with this sigma squared that must be positive and non-infinite or finite. And why are we doing this? Why are we assuming that this is Gaussian and not just, falling into the previous more general framework? Well, I sort of mentioned it in the practical, and it's that if we wish to have likelihood-based procedures, then we need to make assumptions on the distribution, and we can assume that this is Gaussian. That's the absolute baseline. And then you could wonder, well, why would we do likelihood? Well, as we've seen in this course, and you've seen in previous courses, if you were in Cambridge, then the likelihood principle gives you optimal estimators under quite general assumptions, and so why not do it? And in addition to that, we'll also introduce now, as a consequence, as sort of stemming out from the likelihood, a least squares estimator that, of course, we could have motivated differently, not via likelihood, but by doing everything through likelihood, we just unify the presentation. Okay, so let this ARMA process be Gaussian. Let's still assume that it has 0 mean. Okay, so I remind you that we were assuming in the previous lecture that we had 0 mean processes, and so we do here 0 mean with parameters. So let me just introduce some notation. So with parameters, generally we would have this separately, but let me put them together into vectors. So phi underline is going to be phi, sorry, not underline there, just one. And then phi p, so these are the p ones from the AR bit of the ARMA process. And then we also have this theta, that is what you expect. Yeah, so it just contains this, these guys. Yeah. Okay, so now in practice, and this is really important, and I think we may have anticipated it already in the practical, we don't really observe, you know, the whole trajectory of this time series for, you know, infinite, you know, for the whole of the integers, if it were defined for the integers, but instead we just have a finite number of observations, right? So in practice, we don't observe the whole of X, but, you know, without loss of generality, what we observe is some X underline that is going to be X1 to Xn, yeah, for some t, for some n, yeah. Okay, okay, so that's it, yeah. And so because we have, you know, because we want to derive these MLE estimators, then we need to look at the likelihood. Then for the likelihood, you know, we're going to have to compute the covariance. So let's just have the covariance matrix first of all defined. So letting gamma n, which is a function of the parameters that I was introducing before. So these guys, and this guy as well. So this is going to be, by definition, it's going to be given by, this is not very clean, so maybe let's say that letting this with this defined as the following matrix. So we take the autocovariance function and we look at lags, you know, at all of the possible lags, basically. So T and S going from 1 to N, okay? And having this, let's say, just for clarity, be the covariance matrix. Then the PDF of, well, okay, so then the PDF of this X underline is this guy here. So this is going to be given by the usual quantities, yeah, of a Gaussian distribution. So we have 2 pi here to the n, and then the determinant of this covariance matrix. And then we have the exponential here, minus 1/2 of this X bar, which is now lowercase. And then this guy inverse, and then this guy as it is. And so these guys are just any vector in Rn. Okay. Okay, so this is this, yeah. Okay, so this is the PDF, and which means that, you know, we have all we need to derive, so can derive MLEs. Okay, but there is an issue, yeah. This guy, you know, it's not simple in terms of the parameters, yeah, because we need to compute this. So, you know, if we did some Newton-Raphson to optimize this function, then at every iteration of Newton-Raphson, we'd have to evaluate this gamma n, and actually many times there is just simply no closed form. and worse than that, we're going to have to compute the determinant and the inverse, and this is going to be very inefficient. Okay, so let me say, so in terms of parameters, and walls of computing the determinant of this guy and the inverse of this guy is expensive, yeah? Okay, so let's then have a different alternative. So more efficient alternative is as follows. So what is it? Well, we can let me jump to the next page. And so we're going to define this guy to be 0 if we have t equal 1. And then otherwise, this guy is going to be, excuse me, the expectation of xn given, you know, the x1 to the xt minus 1. And this is, of course, if t goes from 2 to n. Okay, so we let this. Then we also let u capital ut be the difference between xt and xn hat. And this is called the teeth innovation. Okay, so we let this, and we also define v t minus 1 to be the variance of this ut. Okay. Okay, so then letting lowercase u t be, you know, what we have in the other one. So this would be, okay, so this is, oh, no. Okay, so so this guy is, of course, you know, is lowercase t xt minus the expectation. Well, okay, so it depends on whether this is t equal 1 or not. But okay, so maybe let's say, you know, so if t is greater than or equal to 2, then we have the expectation of xt. This is capital. But now we have x1 being x1 up to xt minus 1 being xt minus 1. Okay, so letting this, we have that, so it can be shown, even though we're not going to show it, but it can be shown that the PDF that we wrote earlier, which is, you know, depending on these parameters, this is going to be given by the following quantity, alternative quantities. This is 2 pi n, and then rather than the determinant, we have the product from 1 to n of the v's. Okay, and then here we get minus 1/2 of the sum of, so from 1 to n of the ut squared divided by the vt minus 1. Okay, and this is still, of course, for x, you know, in Rn. So that's the, so actually let me just write just so that it sounds better. So letting this, then we have 3 things. Yeah, so we have this, we have also that vt minus 1 can be written as sigma squared times rt for some rt strictly positive and for all these guys, and you know, and rt and ut, so both of them only depend. Yeah, okay, I think prefer to say this. Yeah, so only depend on this and this, as opposed to those two and sigma squared. And, you know, very importantly, and can be computed. Actually, let me just remove that comma because I wish to say that these two can be computed. Not the parameters, but the UT and the RT can be computed using an algorithm that we're not going to see, but so efficiently via the so-called innovations algorithm. So this is non-examinable algorithm because we're not even talking about it. Okay. I mean, I wish to emphasize that it is the algorithm that is not examinable, but not really this discussion that I'm having here. Yeah, the discussion should be, you know, you should all be sort of happy with it because there's just like principles. Yeah? Okay, so let's now okay, so let's derive then the estimators really. So given that we can compute this likelihood, we can try to derive the estimators, and so let S, which is a function of these two guys, be defined as, you know, the sum that we had in above. So this guy, and this actually should be the capitals, VT minus 1. Okay, so let this then the MLEs are given by the following. So this guy and this guy are the minimizers. Just to have consistency, say min in capital letters over this and this of the log of S over N. And you should check this, by the way. I mean, it's just a very simple calculation that you've seen, so you may not even have to, but in case you don't like it, just check it. So this and this, so this should be S over N, okay? And the LSEs, as I was saying before, so the least squares estimators are, you know, we wish to minimize this sum of squares. And so what we have here as the equivalent quantity is this S, okay? So then let us call them tildes. This is going to be the argmin over this of the S, okay? And then for the sigma, we take, very clean, we take S over N minus P minus Q. Yeah. Okay. So again, you know, for these LSCs, we didn't really need the likelihood to start with, and we could have guessed, you know, something like this just by generalizing or just by considering, you know, least squares as one would do with the normal linear model, or with the linear model, excuse me, and not the normal one. And so it's the same story here, but we need to account for, you know, if you go up and see, you know, this guy, well, this sum of squares is no more than this this quantity. So, this quantity is no more than this quantity here. Yeah, close that properly. And so we are minimizing the squares, as we would have done with least squares in the linear model. But here we're accounting for those dependencies that I was emphasizing that were, crucially different, or making the time series crucially different from the linear models. Okay. And I don't know if I mentioned it, but here the x is there in this way because there is no mean, because the mean is 0. Yeah? Otherwise, we'd be subtracting the mean. Anyway, okay, so we have this, and so we can now move on to inference. So 3, 3, 2 inference. Okay, so the first thing to say is, well, we could try to now have some inferential procedures for these parameters that we were looking at. And so let's say that if x is armor with PQ, but it is also Gaussian, causal, and invertible, then the MLEs and the LSEs are, they're asymptotically normal. So we have the asymptotic normality of MLE, as you would expect, because this model is regular. So they're asymptotically normal, and they are efficient. Yeah. So they achieve the Cramer-Rao lower bound in this problem. Okay, and then what is quite remarkable actually is that, remarkably, the limits, so this, this Cramer-Rao lower bound, the value of it, then it does not, or the limits do not change if we drop the Gaussianity assumption. What do I mean by this? Well, I just mean that, you could try to compute the expectation of the negative Hessian of the log likelihood, and then with that, you would get the Cramer-Rao lower bound when, under Gaussianity, and that would be, the sort of limiting covariance or the limiting variance, and they would be asymptotically normal under the Gaussianity assumption, but it turns out that you can just keep that, that normal distribution with that variance, even when you don't have the Gaussianity assumption. Yeah, so you will have that as the limiting distribution. It doesn't mean that they are efficient, because we're not, we're not assuming any distributional assumption anymore, but you get that as a limit. And this, by the way, in practice means that if we are using R, say, and we get these standard deviations for a coefficient, and so we build the confidence intervals, say, for instance, then these are going to be valid not only under the Gaussianity assumption. Yeah, that's what is important about it. Yeah. Okay, so I don't include it here because actually it's it's not a clean expression, and you can just work it out as well. I wouldn't tell you to do it, but it can be it can be I guess computed, if you like, via this negative, well, or via the usual calculation of the Fisher information matrix. Yeah. Okay. So So I did claim that we were going to see, you know, how to test ARIMA or ARMA versus ARIMA with D greater than 0. So let's do that now. So, you know, so far we've talked about ARMA only. So what if, you know, we sort of guess or have some evidence that the series is not stationary and that the non-stationarity can be understood via an ARIMA process. So let's test this situation. So stationarity. Okay, stationarity or unit root test. In this case only is called also unit root. I will mention this in a sec. Why this is. Okay, so if we can, as I'm just saying, we can try to test. So I mean, of course, we could test stationarity in many ways. So we could, you know, as in we could take it as the null distribution just having stationarity, or we could take a stationary family of models as the null hypothesis, which is what we're going to do, which is a bit more concrete. And then we also need to define the alternative. So we could have, you know, stationary versus non-stationary, but that would be a bit difficult. And instead, what we do is just test within the ARIMA framework. Yeah. And so within the ARIMA framework, what we have is the following. Yeah. So we have that we can test, you know, the null model, therefore, is going to be an ARMA process. It cannot be anything else within the ARIMA framework, I mean, and it's got to be versus an ARIMA with parameter D greater than 0, yeah, strictly greater than 0. Yeah? So we can do this via the so-called KPSS. So this is, you know, this is just the letters of the author, so you will get a reference in the theory notes, and we can also call it the unit root test. Okay, and then and it makes sense that we call it now unit root test, because what we are testing is precisely a unit root. Yeah, remember, for stationarity we needed this unit root in the AR models, and which is, you know, really where the lack of stationarity can come from. But anyway, you know, earlier I said that the stationarity test, we can call it the unit root test, but it's only then within this ARIMA framework that we can call it unit root test to a stationary test. Yeah, otherwise it's not really a unit root test necessarily. Okay, so so what we have in this test is that under H naught, okay, which is this assumption that we have upstairs in there. So we have that if we take the autocovariance at lag 0 and its estimate, and then you know, take it as 1 over, so the inverse of it, and then we take the inverse of n squared and the sum of the following quantity. Maybe let's write here this, that'd be a bit cleaner. And then we have the sum from 1 to t of x s minus t times the average of all of the values, and then square this. Then this is going to converge in distribution as n goes to infinity to a to the integral of the following dr. Okay, and so where x bar is 1 over n of the sum, so just the usual average of the values, and w as wr with R, in 0, 1 is the standard Brownian motion. Yeah. Okay. Okay, so by the way, in case some of you are familiar with stochastic processes, then this has a name. This transformation of the Brownian motion in 0, 1. This is a Brownian bridge. So this is really what we are integrating. Yeah. Anyway, you don't need to know that. But we have this. Yeah. So we have that under the null model. We have this, and so therefore we can try. We can test for a unit root. Yeah, or stationarity within the ARIMA framework. Okay, so that for stationarity, and then let's finish up with forecasting. And let me just. Okay, so forecasting. What is the goal? Okay, so 3, 3, 3. Forecasting. So what is the goal here? I mean, recall that we have data that is just x1 to xn, and what we wish to do is just to predict. So predict, xn plus some h, yeah, for some h greater than 0, so somewhere beyond the last observation from precisely our observations from 1 to n, yeah. Okay, and we wish to do it well, yeah, in some way. I mean, because we could, of course, predict any value, yeah, but it's got to be a reasonably good value. So the same well, yeah. Okay, so this is the goal, and then what is the idea of what we're going to do? So idea is, to stay within the framework that we've seen in the past, which is to find the best linear predictor under the squared error, yeah, for the squared error. Yeah. Okay, so this is just very standard for us. And so in other words, what we wish to do is to find a vector that is going to be, dependent on h, and it's going to have dimension n. That is got to minimizing the following quantity. Let's have a subscript with n. So this quantity is going to be then the squared error. So this is just the xt plus h minus the. So this is. Let me just for a sec. Bear with me with the notation. So this is. Oh no, that's not t. That should be n plus h. Yeah. And this is n plus h as well. This is squared, where Pn x n plus h is defined as this A transpose x bar. Yeah. So we have that, we are trying to minimize the expectation of the squared difference between the actual, random variable at n plus h and the prediction of it from the 1 to the nth, observations. Yeah. So this is why we have the subscript n in P. Yeah. Okay. So just check by differentiating the following. So check that the solution to this is given by a given or a as this capital sigma, so the covariance matrix that we had earlier in the likelihood inverse times some vector, where this vector is defined as the vector of autocovariances from the h lag to the n plus h minus 1. Yeah. Okay. Okay. So good. So we have a way to predict, yeah, that is optimal from in this L2 sense. And so are we done? Yeah? No, we're not, because we need to plug in the data really. Yeah. So far, this A doesn't really depend on data. It just depends on these, quantities that we, depend on parameters that we don't know in advance, of course. And so, what are the issues? Well, that is an issue, but more important issue is that these this guy is now beyond n, yeah, and well, it's even at n and beyond, yeah. And if you look at the sample autocovariance function, then you'll see that you cannot compute it. Yeah, it's not defined for that. So cannot, well, or sample autocovariance function is not defined for for lags that are larger than or equal to n. And then also really bad, because what we could do is to say, well, rather than assuming, rather than taking this as an estimate, let's just compute the form of this gamma x in terms of the parameters, and then let's plug in the MLEs or the LSEs. And that is an issue because we're back to the same issue that we had before, and is that there isn't a closed form, general closed form that you can then use. And also we need to invert this guy in the A, yeah. So the covariance matrix in the A. So that's an issue, yeah. So and this guy as as a function of these parameters, and also this other function that we defined, or vector that we defined as a function of these guys are hard to compute, yeah, or expensive to compute, yeah, expensive. Okay, so just as in estimation, we can instead go via the innovations algorithm. Okay, so instead, if P, so if the maximum between P and Q is strictly less than n, just for simplicity, okay, so this is not needed, otherwise the expression changes. It's complicated unnecessarily for the purpose of the exposition. So for simplicity, we have that the Pn, so this guy, which is the projection of the n plus h guy from the 1 to nth data point, so can be written as follows. Yeah? So as the sum from 1 to p of the AR bit, so that should be an R, and then we have here the projections of the previous values, okay, so minus R, and so this is very similar to the AR sort of expression, and then now we need some sort of more MA expression, and so this is going to be given by the following, so R from 1 to Q, okay, of theta n plus h minus 1, and then we have a second parameter, or a second index, sorry, R, okay. So essentially what we're going to have as we run through different h's and r's is a matrix of parameters theta rather than a vector as we did before. And then this is times the innovations rather than, rather than the epsilons if we were defining an ARMA model. Yeah? Okay, so we have m plus h minus r. Okay, and again, this is for some guys, thetas. Okay, that are reals, which together with the use, okay, so with the use, let's say this, and the sigma n squared h can be computed efficiently with the innovations algorithm. Okay, which is an algorithm yet again that is not examinable, so I'm hiding it under the carpet completely here, and just stating that there is an efficient way of computing this, and actually it's a recursive. So I haven't mentioned this so far, but it's a it's a recursive algorithm, and so you sort of do it sequentially, and this is pretty quick, yeah, for the computer. Okay, and then lastly, so we've spoken about how to forecast or how to predict, but then sometimes we also want to have some inferential procedures for the predictions. So then lastly, for h greater than 0 fixed, we have that the difference between this random variable and its predicted value in whatever way we get it, but with this, so with innovations algorithm, say, then divided, normalized by the variance is actually the standard deviation, yeah, not the variance. So this is going to converge in distribution as n goes to infinity to standard normal distribution, yeah. And so with this we can have, remember that this guy at the denominator can be also computed from the innovations algorithm, and so we can do, of course, with this guy. And so then we have, a way of constructing inferential procedures, say confidence intervals or tests, yeah, arising from those confidence intervals, for instance. Okay, so that is the end of time series, and then on Monday we'll put into practice these concepts and finish off all of the contents of the course. Right, well, thank you for your attention, and see you on Monday then. Bye now.